Welcome back to our lesson on electrochemical cells. The next set of redox reactions we will be looking at have one major difference from galvanic cells. They are not spontaneous. That means that the energy in the form of electricity must be supplied in order for those reactions to take place. In fact, the biggest difference between the two is that galvanic cells turn chemical potential energy into electrical energy. Electrolytic cells turn electrical energy into chemical potential energy. Let's take a look at how that might happen. The best way is to look closely at an example. A battery supplying the electrical energy is connected to two electrodes made from carbon. A solution of copper bromide has copper 2+ ions and bromide ions in solution. The water in the solution should not be ignored either because it can also react sometimes. When a voltage is supplied to the two carbon rods, they conduct the positive and negative potential to the solution. This is where several things happen. Because the cations are positive, they are attracted to the cathode that is negative in electrolytic cells. The anode attracts anions with its positive charge. But before we start reacting anything, let's look at the table of standard electrode potential. Circling water and the ions we talked about shows that copper 2+ is in several places. Circle them both. Twice we circle water and also circle the bromide ion. We see that water doesn't react in this case, and the strongest species are the negative bromide ion. So, here immediately we can see a problem. Even when we select the strongest oxidizing and reducing agents, neither of them is strong enough to make a positive slope between the two. That means that the reaction will need energy. That's the point of an electrolytic cell. So, let's keep following the steps and see where that leads us. Writing down copper 2+ plus 2 electrons goes to copper metal for the reduction half reaction. Then the anode or oxidation reaction happens when 2 bromide ions goes to form bromine and 2 electrons. Cancelling the electrons and adding the half reactions shows something interesting. We should see copper metal forming on the negative electrode and a reddish liquid forming on the positive electrode. Close observation does indeed show that this happens. We are making elements. Let's see if we can predict the products when aluminium iodide is electrolyzed. Applying a positive and negative potential, something is sure to happen. Let's run through the steps. Find the ions and water on the table. Circle the strongest and write out the reactions. When we actually do that, we actually find that aluminium 3+ ions are too weak as an oxidizing agents. Water reacts in this place. This is also the reason it is so difficult to make aluminium metal. Its ions are very difficult to reduce. The iodide ions are the best reducing agent in the mixture. Looking at the two half reactions, it's interesting to see that we have to make two elements again. Iodine at the negative anode and hydrogen at the positive cathode. No aluminium is made by this process. It is a spectator ion. The interesting thing is that any of the metals above water on the redox table can't be refined from a solution of metal salts. You might recognize several really important metals, so we actually need a different way of doing this. The only reason that we dissolve salts in water is to make the ions free to move. This is how we make the ions separate. We can also do this by melting the salts, and that is exactly how some of the reactions making these metals happen. There is a particularly important electrolytic reaction that happens in salt water. When we do electrolysis of very concentrated salt water, we find something very unexpected. Look at the table of standard electrode potential when circling the sodium ions, water and chloride ions. We would expect that water to react to a stronger reactant, especially when compared with chloride ions. But because the placement on the table is close and because the chloride ions are concentrated, they coat the positive anode in a layer, keeping the water away. So, this reaction ends up making hydrogen, as expected, and chlorine gas. This reaction is actually the basis for a very big industry. But you'll have to wait for the next lesson for that.